At least we're on part two. And last time here, we started talking about kind of a really important idea, which is the common ion effect. And the idea of that is when you have either like a weak acid or a weak base, which because they are weak, for example, like acetic acid, which we might have looked at, because they are weak, they will set up an equilibrium in solution. And obviously will dissociate into H plus and acetate in the case of acetic acid, and will produce a certain amount, obviously, of H plus as a result of that dissociation. When we add something else in there with it, like say a sodium acetate is not going to set up an equilibrium because it's a salt. It's a strong electrolyte, and it will break apart into sodium ions and acetate ions. Now, the result of having that sort of extra, if you want to think about it, sodium acetate in there, it is going to provide basically our sodium acetate, which is the common ion that happens in the equilibrium sort of equation. The result of that is Le Chatelier's principle will tell us, since we're essentially adding more of the acetate in this equilibrium, it will cause a shift in equilibrium basically to the left. The result of that in terms of sort of acids and even in terms of bases as well is it will, in the case here of our acid, cause us to have less free H plus in that solution. And in that case, what we will see is we'll actually have less H plus, and we will see the pH kind of go up. And again, it won't go maybe a basic or anything like that, but it will definitely be a higher pH than the pH would be if you just had acetic acid in there alone, due to the presence of this common ion. Now, in a common ion situation, you can, if you need to do a calculation, you can still do our ice table like we've done before. The key, though, obviously, with our common ion here is you do need an initial here. So you'll have initial molarity. This will be 0. And the key is you do need, again, an initial on the other side where the common ion is basically present. Again, otherwise, you would be doing basically just a weak acid sort of ice table. The rest of the table is pretty much the same. And obviously, you could go into your Ka and solve for X. And again, in this case, X would equal the H plus concentration, which would then allow you to get to the pH. Now, what we saw was because of the common ion being present in these type of situations, it causes the weak acid, and again, you can just also do this with a weak base, to not dissociate as much. And what we see is the change that occurs between sort of the initial concentration and ultimately the final concentrations of each of these guys are usually not that big of a change due to the presence of that common ion and really stopping it from breaking apart. And what that allows you to do, as we talked about last time, is if you don't want to kind of use an ice table, if you could recognize that these things are related to each other, and really what you're recognizing in terms of are these things related is basically these guys here. It is basically that Bronsted-Lowry difference of 1H plus basically between them. So if you can recognize that they are related to each other in that sense, you could skip the ice table and you could go with the Henderson-Hasselbalch equation, which is the pH is equal to pKa plus the log of the base over the acid concentration. And the pKa here is minus the log of the Ka. And as we talked about last time, I would personally roll with this equation because, again, you can use it really in any situation, acidic situation, basic situation, neutral situation, whatever it may be. Again, you just got to make sure you have the pKa and the base on top and the acid on the bottom. As I showed you last time, there is a sort of POH version of this equation, and it uses the pKb plus the log of the acid over the base. And sometimes people like to use this one in a more basic situation. But as I mentioned last time, most of the time you're asked for the pH anyway, so you might as well just kind of use that one and be done with it. But It does bring up, though, a nice relationship between these two. And again, if you take the pKa value plus the pKb value, it will equal 14. So that's also a quick way, if you maybe have the Kb, you could calculate the pKb, subtract 14, and you have the pKa that you need maybe for your Henderson-Hasselbalch equation. So you sometimes will see this one, but you still got to do kind of the 14 minus the pOH to get to the pH. So like I said before, just go into the Henderson-Hasselbalch on top and you'd be good shape. Any questions on that here? All right. So I thought we stopped at this one and you're supposed to do it. So let's go through this one here and see what we got going on. We're looking for the pH of a solution that contains 0.3 molar formic acid with 0.52 molar potassium formate. Ka value is 1.7 times 10 to the minus 4. So the first thing I can see is obviously have a weak acid, and the acid should have more hydrogens than the base here. And the base oftentimes will have this sort of spectator ion in it as well. So these two guys are related to each other. We basically got HCOOH and really HCOO minus if you take the potassium out of the way. And again, the difference here, thank you, is 1H plus is the only difference between them. So this is a common ion situation. Also, as we'll talk about in a second, basically a buffer situation as well, which is pretty much the same thing. So you do have two options, like I said. If you wanted to choose still to kind of do the ice table approach, I would take the weak acid and break it apart like you're doing a Ka problem, and this would break apart into H plus and formate here. And initially here we have 0.3 molar of our formic acid. We have 0 here. Remember, though, with the potassium formate there, that is going to break apart into potassium ion and a formate ion. And again, that is not going to set up an equilibrium because it's an ionic compound. It's a strong electrolyte. But we do know the concentration of the whole thing here is 0.52 molar, and it's a 1-to-1 relationship between the whole thing and formate. And that would mean that the concentration here is also 0.52 for our common ion. So this would be obviously our common ion here. And the most important thing, if you do choose to sort of do an ice table for this type of calculation, is that entry right there. Once again, if you kind of zero it out, you are not doing this calculation. You're just doing a weak acid calculation. So a super common error when people kind of do the ice table here. Minus X plus X plus X. And we go to equilibrium here, 0.3 minus X, X, 0.52 plus X. At this point, you would go to your Ka, you would solve for X, and X would equal the H plus concentration, which then would allow to get you to the pH. Now, alternative to that is what we've been talking about, which is I recognize that these two things are basically related to each other and really a buffer situation and common ion situation. That means I really don't need to do the ice table in this case. I could go right into the pH is equal to the pKa plus the log of the base over the acid. Here I do need to calculate my pKa value. So my pKa is minus the log of the Ka value, and that is minus the log of 1.7 times 10 to the minus 4. And that's going to get me here, looks like 3.77, we'll call it. And putting that in here, my pH would equal 3.77 plus the log. Again, a reminder that this obviously is our acid. It has one more hydrogen. This guy's got kind of like a spectator ion there. A lot of times that's your base. So I do want to go 0.52 up on top and 0.3 on the bottom, which would give me the concentration of my base over my acid. I'm going to take 0.52 divided by 0.3, take a little log action of it, and then add it to 3.77. And that is going to get me here a pH of 4.01. Now that should be the exact same pH you get, obviously, if you went through the ice table and solved it kind of using the ice table. Any questions on that there? So as we talked about last time, this definitely can save you some time if you could recognize that it is this sort of common ion buffer situation that's occurring. But we also talked about last time a really important thing with this formula, which is you should not use it in all situations. So you should only use it really in buffer situations, which are common ion situations. Other than that, you should not use it. You should do probably an ice table and stuff like that. If you don't want to worry about using it in the wrong situation, you could just do the ice table. Again, you could always do an ice table. It works in all situations. But again, don't use that for every calculation. Any questions? All right, so we've been talking about this. So let's talk officially about really what we've been talking about, which is common ion. And really, a common ion is basically a buffer situation. And a buffer and a common ion is the same idea. So a buffer is a solution that's made up of one of two sort of combinations. You can make a buffer with a combination of a weak acid and its conjugate base, and is oftentimes referred to as the salt of this conjugate base. And the salt part just means it's got like a sodium or something like we saw in the previous one, a potassium kind of hanging out there. Or you can definitely make a buffer out of a combination of a weak base and the salt of its conjugate acid. And both of those things need to be in the solution to begin with in order for a buffer to work correctly. You cannot have a buffer that is made out of a strong acid or a strong base. So you cannot have a buffer that's made out of a strong acid or strong base. It will not be a buffer. Although we'll talk about it, you can use it to make a buffer, but it cannot still be present to be the actual buffer. So what does that mean? It means basically both of those things need to be in solution at the beginning, and that's really important for how a buffer works. But let's first talk about what a buffer is, and sometimes, again, people have the wrong idea about what a buffer is. Sometimes people think a buffer is a neutral solution, and it can be, but you could also have a buffer that's acidic. You could also have a basic buffer as well. You could actually make a buffer at any pH that you choose, and you'll do that in a couple experiments from now. You'll make a buffer at a different pH. What a buffer is whatever pH your buffer is, it's able to resist really big changes in pH when you add additional H plus or additional acid or base to that solution. So when you add additional acid or base to that solution, your buffer is basically able to hang out at the pH it's at. So let's just say you had a buffer at a pH of 4 and you added acid to it. It will hang out around 4. It probably go down a little, maybe 3.9-ish or something like that, but it will not go from like a pH of 4 all the way down to like a pH of 1 if you made a good buffer. And if you had a buffer at 4 and you added some sodium hydroxide to it, it might go up a little bit. Maybe it goes to 4.1, 402, something like that. But it will not go from like a pH of 4 all the way up to like a pH of 12. So you won't get these really big jumps in pH. It will move a little bit, as we'll talk about. But overall, it's able to resist really big jumps in pH when you add additional acid or base to it. And again, what it's made out of is essential for that happening. So in order for a buffer to work, you need to have basically a weak acid or a weak base. So for example, we'll go with acetic acid here on this one. And because you have this weak acid, it is actually going to be the one that sets up this equilibrium in solution, right? Arrows and all in the beaker. So it will set up this equilibrium. And when you make something like this, if you made like an acetic acid, sodium acetate buffer, the relationship between these two things is a weak acid and this conjugate base. And remember that this sodium acetate is really sodium ion and acetate ion. So it's actually the conjugate base is the acetate. And that is the relationship that really is the buffer part of this solution is those two things. They are related to each other by 1H plus, just like Bronsted-Lowry definition. and that is a weak acid and its conjugate base. And when you make this buffer, you basically have both of those things in there. You have an acid part to the buffer, and you have a base part basically to the buffer. And they both are in that solution at the beginning in pretty good concentrations because, for example, if you were to make this, you would take some acetic acid and you would dump some extra sodium acetate in there to kind of beef up the acetate part, and you'll have a pretty good amount of each of those in there. Now, it's really important that both of those things are in there in order to function as a buffer to begin with. The reason you cannot, for example, have a buffer that is made out of a strong acid or a strong base. Let's just say we wanted to make a hydrochloric acid sodium chloride buffer, right? So this is a strong acid. And again, that's a salt, which is basically sodium and chloride. So really our buffer that we hope for would be basically these two things. Again, this would be as conjugate base in this case. Now, when we go to dump this into our beaker, if we wanted to make our hydrochloric acid chloride buffer, probably not going to happen there. We'll put on happy face. When we put that HCl in there, what's going to happen, because it's a strong acid, it is not going to set up that equilibrium, which means it's just going to break apart. And what you're going to have is just H plus and chloride ions floating around. You will not have an acid that sets up the equilibrium. Then when you add maybe some sodium chloride in there, well, frankly, you're just adding more chloride and some sodium ions, right? So in this case, the only thing you really have floating around in that solution is the conjugate base. You don't have an acid part because, frankly, it broke apart. Here on our weak acid, we are able to keep the actual acid part of the buffer in solution. We're able to keep the base part of the buffer in solution because they're weak, and that will keep them both in solution. So that is why a strong acid or a strong base cannot be a component of a buffer, because you will only have basically one part of the buffer that's needed for it to function correctly. And in this case, you would have just really the conjugate base floating around. You have no acid part. So it would not be able to function well as a buffer. And you would actually see a pretty big jump in pH here, because if you added more acid, you're just increasing the amount of H plus in that solution. So the pH is going to definitely jump a lot because there's nothing that can basically handle that influx of H plus. So this is why, again, a strong acid or strong base cannot be a buffer. But as I mentioned before, we will talk about it. You can use it to make a buffer, but the strong acid or strong base is not part of the buffer to begin with. So how does a buffer actually work to prevent really big jumps in pH? Let's take a look at something that's not a buffer, which is water. So water is not a buffer. And let's say that in water, we wanted to add some hydrochloric acid, right? So here's my beaker of water. And here I'm going to add some hydrochloric acid to it. And as I just mentioned a second ago, what's going to happen when the hydrochloric acid basically goes for a swim is it is going to completely break apart, as it's a strong acid, H plus and Cl minus. So at this point, what you just did is you just introduced into this solution a lot of free H pluses really, really quickly. So we have a lot of free H pluses. And that's going to definitely have a big effect on the pH, which is minus the log of the H plus. What we just did is essentially make our H plus concentration increase. That's going to make our OH minus concentration decrease. And the result of that is when the H plus concentration goes up, the pH is going to drop a lot here. So if we started, for example, we had pure water and it had a pH of 7, doubt it. But when you add the acid to it, it'll go maybe from a pH of 7 down to like a pH of 2 or maybe 3 or 1, depending on how much you added. So you'll see a really big jump in pH, and that's because you have just introduced into that water, which is not a buffer, a lot of H plus really quickly, and that's going to cause a very big jump in pH. Now, let's say that we added sodium hydroxide here to our water. And same idea here, if we had sort of a beaker of water and we added some sodium hydroxide, it is a strong base, which means it is going to break apart into sodium ions and a bunch of hydroxide ions. So it will also completely break apart in water and create our sodium ions and our hydroxide ions. And once again, it's going to create a lot of free OH minus in that solution. And that's going to cause the concentration of OH minus to increase by default. Because they work together, the H plus concentration will go down. And here we would see the pH definitely go up, as we have introduced a lot of OH minus in this case. So again, if we had a pH of 7 for our water and we added this, we might be up to like a pH of 12 or 11, or a very big jump in pH. And that's because basically we have produced, in the case of the acid, a lot of free H plus in there. And in the case of the base, a lot of OH minus, which will also affect, obviously, the H plus concentration. Any questions on that? So this is why in a non-buffer situation, if you add an acid or base, you would expect a fairly big jump in pH, because you're just introducing those two things, either H plus or OH minus, depending on what you add. So what happens if we add these exact same things to a buffer situation? And we'll look at, say, hydrofluoric acid and a little sodium fluoride. That is also a buffer. That is a weak acid. And this is his conjugate base, really the salt of his conjugate base. That sodium makes it the salt. The sodium, by the way, again, is not doing anything. It is really this guy and this guy that are our buffer in this case, right? It is basically that F minus. Again, the difference there is our 1H plus difference between HF and F minus. Our Bronsted-Lowry difference allows it to be a buffer, as they are related to each other in this case. So it's basically our weak acid and our conjugate base. So let's say we took our buffer here, and again, the buffer here to begin with, solution will have that weak acid, which is hydrofluoric acid, and it will set up that equilibrium there, and we'll have basically these guys floating around in solution to begin with. And once again, we have our acid part of our buffer in the solution, and we have our base part of the buffer here in the solution. And again, like I said, if you're going to make this, you would dump a little bit of sodium fluoride in there to kind of beef up the F minus in that solution, and you have a good amount of each of those. So now when I take my hydrochloric acid and I want to add it to the solution, what we're going to end up with is actually a reaction. So my hydrochloric acid will actually react with my buffer in this case. Should it react with the acid part of the buffer or the base part of the buffer? They are called what type of reactions? Acid base reactions, yeah? So if I add an acid, it's not going to go react with the acid. It's going to go find the base part of the buffer. And you will get a reaction, and I'll use the sodium. You can take it out if you want. You're going to get basically a double displacement reaction that's going to happen in this case. They're going to switch partners. And when this occurs, we will make HF, and we will make a little sodium chloride at this point. So when we do this, again, that HCl is a source of H plus and Cl minus coming in. We are going to get basically a reaction that's going to occur. So the first thing that you should see is here on the product side of this reaction, we actually formed HF, and that is part of the buffer to begin with. And that always happens when you have a buffer. You will actually use part of the buffer, and then you'll make the other part. So the other part of the buffer is always sort of made as a reaction that occurs. So clearly that's not going to kind of screw up the pH too much. We also have this guy, which is a salt. And we know from our previous conversation that salt is what type of salt? That is a neutral salt, right? It's a pH of 7, right? It's neutral. Sodium group 1, right? Chloride coming from hydrochloric acid, which is a strong acid, means that it is not going to affect the pH. So we made basically part of the buffer as a result of this. We also made a salt that's neutral, that's not going to really screw up the pH. But it is actually what we don't see here that's really important. And what do we not see here that we did see when we added hydrochloric acid to water? What is not present on that side? We do not see any free H plus that was formed. So when we added this acid to our buffer, we do not see any free H plus formed. And that's really important because essentially that means that the concentration of H plus that we started with is relatively constant. And if my H plus concentration I started with is relatively constant, that means my pH will also be relatively constant. Now, I say relatively constant because you are making a little bit more HF, which will provide perhaps a little bit more H plus, and you will actually see the pH go maybe down a little bit, but you will not see a giant jump in pH downward. So maybe again, if we start at a pH of 5, maybe we end up at like a pH of 4.9 something, so a small little decrease because, we did add acid. It is going to increase a little bit of the H plus, but we will not see it jump from like 5 all the way down to 2 because basically there is no really big influx of H plus by itself in this case. So when this goes for a swim, the bad thing for the pH is that H plus is coming in. And in this case, what happens is this H plus will go and find our F minus, and the result of that is it will make some HF in this case. And again, it's not allowed to, like it was in water, just freely float around and have a big effect on the pH. So it sort of gets gobbled up in that sense. Any questions on that there? Yeah.
Reaction to like just a straightforward one, or is it still kind of
So to answer your question, the HCl, because it's a strong acid and a strong electrolyte, is always a one-way street. So it's basically in this case just a source of what you're dumping in is H plus and Cl minus. In terms of our buffer there, it is still sort of a reversible reaction happening in there. And again, obviously there's no errors in the beaker or anything like that. But in terms of the equation, that equilibrium is still set up in that beaker. And it's going to basically react with something like that. And that's caused a little bit of a Le Chatelier's principle to occur. But the buffer equilibrium is still there. But what you're adding in terms of a strong acid or strong base is always just sort of a strong electrolyte, and it will never set up an equilibrium. And again, that's why they cannot be used as a buffer because they're not able to keep both of those things in solution. They're basically just going to break apart. So you should think of sort of the acid or bases of what's being added as just sort of like a source of those two things coming into the solution. Yeah. Other questions? All right, so let's take a look at what happens if we take the same buffer here and we add in some base to it to see our sort of situation. So once again here to begin with, we would have our buffer. And because we have our weak acid, again, it's going to set up the equilibrium here. And just like previously, we have our acid part of our buffer. And we have our base part of our buffer. And again, that is key for how a buffer really works, is having both of those things in there. So now we take some sodium hydroxide here, which again is a strong base, and we're going to add that in. And once again, this is basically a source of sodium ions and hydroxide ions because it's a strong electrolyte going to be dropping in. And in this case, when we add the sodium hydroxide to this buffer, and again, this is our weak acid and our conjugate base. Because sodium hydroxide is a base, it is ultimately going to react with the acid part of the buffer. So we're going to get basically an acid-base reaction that's going to occur in this case. Also a double displacement, right? Plus, minus, plus, minus. And we're going to switch partners. And we're going to make a little sodium fluoride and a little H2O, right? Put that in there. And now what we see is something similar to what we saw when we added the acid to this buffer. We actually made some sodium fluoride, which obviously is part of the buffer to begin with. So that's not going to really screw up the pH all that much. And again, like I said, it's ultimately how a buffer kind of functions. And able to function over a long period of time is you kind of use up a little, but make the other part. So it's almost self-regenerating part of it as you use it up. We obviously made water, which should not mess up the pH here either. And again, much like the previous one, is what we don't see here that we did see when we added this sodium hydroxide to water, and that is we do not see all that free OH minus that was freely floating around when we added it to water. In this case, when we look at our reaction here, we don't see any free OH minus formed. And that's really important because the OH minus concentration remains relatively constant. And because OH minus and H plus are related to each other, right? As one goes up, the other goes down. That would mean that since my OH minus didn't really move all that much, the H plus concentration will remain relatively constant. And that will then give us a relatively constant pH as well. So again here, will you actually see the pH move? If you have like a pH meter in there, you will. Again, it will go up a little bit because you did add base, but it will not do any big jumps from, again, like a pH of 5 to a pH of 12. You won't see that big jump. So in this case, what happens is it's our OH minus. It's our OH minus basically coming in and making water here, right? And getting tied up in there in the formation of water in that particular case. And again, we're making a little bit more of the F minus. So this is really how a buffer is able to essentially keep a pH relatively constant, even when you add additional acid or base to it, because it has both of those things in the buffer solution to begin with, an acid part and a base part. When you add additional acid in, it's able to prevent the formation of free H plus by reacting with the base part of the buffer. And when you add base to that buffer, it's able to prevent the formation of free OH minus by reacting with the acid part of the buffer. I'm sorry, I put my arrow on the wrong spot there. Basically, it'll go there to make water. So ultimately what that's able to do and really what makes a buffer work is, again, that ability to uh, prevent the formation of free H plus or free OH minus. So a buffer is able to resist that change by preventing the formation of free H plus if you add acid, or free OH minus if you add base to a solution. Any questions on that there? This is also why, as I mentioned earlier, if you were trying to make your hydrochloric acid chloride buffer work, as we talked about, you basically have H plus and Cl minus in there to begin with. So what happens in this particular case is if you were thinking this was going to work as a buffer, as I mentioned, you only really have the base part. And when you add HCl in there again, that is going to be a source of H plus and Cl minus. So what you're basically just doing is piling on some more free H plus when you do that. And again, that's why you're going to see a really big jump in pH, because this cannot do anything with it other than let it float around freely in that solution. And again, that is why this would not be able to work as a buffer, having it as a strong acid. Any questions on that? So ultimately what we see here is typically you can make a buffer. And a lot of times when you make a buffer, and you think about sort of the Henderson-Hasselbalch equation, which is used for buffers because buffers are essentially common ions, like we saw there, HF and F minus, right? And acetic acid and acetate, they are basically common ions. So if you make a buffer, a lot of times you'll make kind of your acid part of your buffer and maybe your base part of your buffer relatively equal to each other in terms of their concentration. And what we see here is if you add acid to this buffer, it is going to react with the base part of the buffer, and dramatically drawn here is going to increase the acid part of your buffer, and it's going to decrease your base part of your buffer, right? And same thing, if you add base to your buffer, additional base, it will react with the acid part, and dramatically drawn here, it will increase the base part of your buffer and decrease the acid part of your buffer. So again, it typically will use up part of the buffer in the reaction, but always it will make the other part of the buffer as a result of that reaction. So like I said, you kind of use part of it up, but then make the other part of the buffer as a result of that reaction. Now, there is a thing that is known as buffer capacity, and there is a limit to how good your buffer would be. So let's just say, for example, you went to add acid and the instructions said, we'll add 0.1 molar HCl, and you found the bottle of 18 molar HCl and decided that seems a good idea. Pretty close. They both have a 1 in it. They're probably about the same. So you decide, hey, I'm going to add some HCl, really strong HCl to it. Or even if you add this guy, right? What's going to happen in this situation is, let's just say I just keep adding acid. Every time I add acid in the situation here, I am going to be chewing up, right, my base part. Although this part will get bigger, I will keep chewing up my base part, right? And if I keep adding, eventually what will happen to my base part? It will go away, basically, right? And you'll blow through it. And if you blow through the base part of this buffer, that's a bad situation if you keep adding acid, because at that point, you're now just adding a bunch of H plus into that solution. And at that point, once you blow through your buffer, you will then see a pretty big jump in pH. So you'll see the pH actually change a lot at that point. It is possible to blow through your buffer. You could do it a lot quicker by perhaps grabbing this guy and starting adding that, because that's just going to add a lot of H plus really quickly, and that's just going to use up the base part of your buffer very, very quickly. So when you make a buffer, it's really important to not only make a buffer correctly, but correctly in the sense of its concentration to be able to handle whatever acid or base you're going to put in there. Not all buffers can handle certain acids and certain concentrations of acids. So the concentration of your buffer is actually really important as well. If you're adding something that's a significantly strong acid, high concentrated acid, you would need probably a pretty high buffer concentration to handle that influx of H plus. You have a really low buffer concentration, you have that, it's just going to kind of blow through it. Now, same thing here, if I were on this side and I could just keep adding base, we're just going to keep chewing up our acid part. Again, we'll make more of that, but eventually we'll blow right through, right? So this can happen, is really important, and you've probably have seen that, and we'll talk why that happens in a bit. But maybe when you did titrations, this is what's occurring in some titrations. You actually make a buffer and then you blow through it, and you probably saw that as a result of maybe you had no pink in your titration, all of a sudden it became super pink, right, really quickly. And we're going to talk about why that happens when we get to titrations next. But that does sometimes happen. So buffers have a capacity. And again, the molarity of the buffer and what it's made out of is right. So how do you know how or what you should make a buffer out of? Well, if I were to make a buffer where I had pretty much equal concentrations of the acid part and the base part, if we look at the Henderson-Hasselbalch equation, that would give me the pKa plus the log of, we'll just call it 1/1, which basically would give me the pH is equal to the pKa plus the log of 1, right? If it was the same concentration on top or bottom. And the log of 1 is equal to 0, yes. And that means the pH is equal to the pKa. And typically speaking, you would want to choose a weak acid or a weak base that has a pKa value plus or minus 1 of your desired pH. So if you wanted to make a buffer at a pH of 4, acetic acid would be a great choice for you, as the pKa is like 4.74. That's pretty close. That would be a great one. Ammonia would be a terrible choice, as the pKa is like 9.25. That's pretty far away from your desired like buffer of 4. You're going to have a really hard time to get that to work. So to choose sort of what you should make it out of, you should look at the pKa values of weak acids or weak bases and choose one that is as close to your desired pH as you could find or have available to you. And you can calculate and make your pH or your buffer out of that solution. Any questions on how buffers work? All right. And as I mentioned before, buffers are obviously a common ion situation. And this is really the place where if you have a buffer situation, you could use the Henderson-Hasselbalch equation. And that is really where you should only use it, is if it is a buffer situation. All right, so as we can see here in this case, our non-buffer solution, again, water, because of the production of that free H plus, we're going to see a significant change in pH. So this is water, which is not a buffer. When we add HCl to it, you can see a giant drop in pH. It goes from like a pH of 7 down to like a pH of 2-ish, or 1 and some change. And again, that is because we are just unloading a lot of H plus into that solution. If we add that to our buffer, we get this reaction that occurs. And again, no free H plus there. And no free H plus keeps, again, our pH relatively constant. All right, let's take a look. So again, in order to determine can it be a buffer, really two things you want to look at is we know it needs to be a weak acid as conjugate base, or a weak base in its conjugate acid. Acid conjugate base, or a weak base and its conjugate acid. What that basically means is we're looking for really an H plus difference between those two things, right? And it has to be weak. So remember, we can't have any strong type stuff. So if we look at A, we have basically HF and KF. And basically, this is a salt, which means it's K plus and F minus. And now if we look at these two things, the difference there is 1H plus, which is one of the things we need it to be. And we hopefully know this is not one of our 6 strong acids. So I would guess that that's a weak acid in this case, and that would be its conjugate base. And that would check off that this could be a buffer. It's pretty much the same buffer we just did in that example that I worked out. Any questions on that there? How about B? We take a look at B. We got basically HBr. And again, the one with the more hydrogens is the acid, and this would be KBr, which again is a salt, which again is K plus and Br minus. So again, if we look at this and this is an acid. This would be its conjugate base, and that is an H plus difference, so that is good. The HBr is what type of acid? It is a strong acid. It's one of those 6, so that is not good. So this cannot be a buffer, again, because it is a strong acid. So even though they are related to each other by 1H plus, you cannot have, again, a buffer that is composed of a strong acid or a strong base. As we talked about earlier, it will not be able to set up that equilibrium. It will not be able to keep both the acid part and the base part of the buffer in solution at the same time. Any questions on that one? And see here, we got some sodium hydrogen carbonate. and a little sodium carbonate here. There's actually two salts, and is sodium ion and a bicarbonate. I'll put a slash there. This guy is some sodium and carbonate here. And the buffer is, if it is a buffer between these two things, right? These two things have an H plus difference. And this is going to be the weaker acid, right? As it also has the H, extra H, it makes it possible for it to be an acid. So that's going to be a weak acid and its conjugate base. So yes, that is going to be a buffer. How do I know that is probably a weak acid? Well, if I just think about what carbonate looks like, hydrogen carbonate, it perhaps looks like carbonic acid is probably where it originally originated from. And carbonic acid is not one of those 6 strong acids, so it most likely is going to be a weak acid where it came from. And probably in this situation, a hydrogen with a negative is going to be something that's going to be weak in that situation. Any questions on that there? So it looks like A and C there can be buffers to each other. All right. All right, so let's try one here. Calculate the pH of buffer that contains 1 molar acetic acid and 1 molar sodium acetate. The Ka value for acetic acid, 1.8. Okay, let's take a look at it. So we're looking for the pH of our buffer here in part 1. So we basically got 1 molar acetic acid and 1 molar sodium acetate. And we do have a Ka value here of 1.8 times 10 to the minus 5. So even if it did not tell us it was a buffer, we do see a weak acid. And again, we know it's a weak acid because we do have obviously a Ka value associated with us. We have this salt here, which again is basically sodium ion and acetate ion. And that relationship between this guy and this guy meets our definition that we need. It is just 1 H plus difference, and it is a weak acid involved. So that tells us it's definitely going to be a buffer. Again, not always will the problem tell you this is a buffer. So they'll just kind of tell you, hey, you made it out of these two things. What's the pH? So you have to be able to sometimes recognize that you are dealing with a buffer situation. And again, that's the things you kind of want to think about. So since it is a buffer situation, we know it's a common ion situation, which does give us two options as to how you could solve this. You could either do the ice table or we could use the Henderson-Hasselbalch equation. So again, I'm going to use the Henderson-Hasselbalch equation ultimately, but just a reminder that if you wanted to use the ice table, you would most likely set up your ice table with the acetic acid equilibrium. And again, the key here would be in that initial line, you would have 1 molar here, 0, and you need that 1 molar again on that side of the table in order for it to be correct. Obviously, the rest of the table would be like normal, minus x, plus x, and 1 minus x, x, and 1 plus x. Again, here you go into your Ka and get x, and that would equal the H plus concentration, and then you could go to your pH at that point. But again, I'm going to skip that part and know, again, recognizing that it is a buffer, I'm just going to go right into the Henderson-Hasselbalch equation. And really the only thing I need to sort of calculate in this case is the pKa value. So my pKa value is minus the log of 1.8 times 10 to the minus 5 should give us a 4.74 pKa. That will give us the pH is equal to 4.74 plus the log. In this case, you can't really screw up since they're both the same concentration. But again, a reminder that the one with the extra H should be the acid. And a lot of times the other guy will have some type of spectator ion present. So we're going to go 1 over 1 here. And the log of 1 will equal 0. That means in this case, our pH should equal 4.74. It would be acidic in this particular case. Any questions there? All right, so now let's talk about what happens in part B here. And in part B, we want to take basically the exact same buffer system, but in this case, we want to see what happens to the pH after we actually add some acid to it. In this case, we're going to add 0.1 molar hydrochloric acid. For part B, and only for part B, we're just going to assume for this problem that all the volumes for everybody is just going to always be 1 liter. And that's not always the case. You have to take the volumes into account. But just to explain sort of the calculation that's going to sort of need to be done in this case, we're just going to kind of keep it simple by keeping everybody's volume 1 liter. Now, one of the important things that happens in this case is you're going to have a buffer here, and you're going to add some acid to it. Now, when I add volume to volume of stuff, does the molarity stay the same? When you add a bunch of solutions together, do all their molarities stay the same? They do not, right? Like in a lot of our labs, right? We put all that stuff in those test tubes. They are not the same concentration as they were in the bottle you got it from, right? Because you basically did a dilution. And in order to get the right one, right, you had to do the sort of the dilution equation. So whenever we add volume to volume, the molarity, which is basically the moles of solute over liters of solution, changes. But what does stay the same is actually the moles of solute. The moles of solute stays the same. And by the way, the solute is really what is reacting. So when you have a solution, the solute that's floating around in that solution is really the active part of that solution. It's the stuff that's going to actually do the reaction. So whenever you have a situation like we would have in this situation here, where we are adding some more acid or base to a buffer, we're basically adding volume to volume, you need to do your ice table in moles because those will remain the same and not molarity. After you do the ice table, you should, very good habit-wise, convert back to molarity after the ice table. And how would you convert back to molarity? You would take the moles that you got right and divide it by the total volume. So basically whatever you added and what you started with, you take your total volume to do that. So this happens a lot, obviously, in this situation where we are adding some acid or base to a buffer or adding volume to volume. This happens nonstop when you're doing a titration, right? Because in a titration, all you're doing is consistently just keeps on adding solution, right? Until you find your endpoint or whatever it may be. So you're constantly adding volume to volume. So always in a situation, it is good practice, and you should do your ice table of moles when you're adding volume to volume. It's also just as important after you do, and it's usually the first ice table you might have to do. After you do that first ice table to convert it back to molarity afterwards. That way, when you continue on with your calculation, your number will actually be probably in the right unit it needs to be in. So you definitely want to make sure that you do that. So let's take a look at this and see how this sort of works. So we basically have the same buffer happening. We got our 1 molar acetic acid. And we have our 1 molar sodium acetate. And we have our Ka value that's still the same. And in this case, we are going to add an additional 0.1 molar HCl to it. So as I mentioned before, this is not always the case, but we are going to, in this problem, just to kind of keep it a little bit simpler, we're going to assume that everybody's volume just stays at 1 liter all the time. So we're just going to assume 1 liter all the time. And again, that is definitely not always the case. You still have to take the volume into account. So we definitely have, in this case, our buffer, which would be our acetic acid, our H plus, and our acetate, right? That's our buffer. And again, we have our acid part of our buffer, and we have our base part of our buffer in this case. And to this, we're going to add some HCl. So as we talked about earlier, that HCl is basically H plus and Cl minus. So as we talked about earlier, when we add that H plus, it should actually do a reaction, right? And it's going to react with the base part of our buffer, which in this case is our sodium acetate, right? That's this guy down here. So when you add that H plus, it's going to react with the sodium acetate. So we'll get this reaction here of our sodium acetate. Again, it's going to do a double displacement reaction, and we will always make the other part of the buffer, which is acetic acid. So if you're not sure what it makes, it should always make the other part of the buffer, which is usually in the problem. And you're going to have some sodium chloride there as well. Some rain, it sounds like, yeah. Hopefully, hopefully not coming through the ceiling soon. All right, so at this point, this is our reaction, and we're going to do an ice table. And since we are adding volume here, we are going to do this ice table in moles. So we're just going to keep everybody at 1 liter. So basically that means that we have 0.1 moles of HCl, 1 mole of sodium acetate. And also really important when you do this ice table, not to forget on the right-hand side here, we still got 1 mole of that, right? If I didn't put the guy on the right, am I doing a buffer problem? I am not doing a buffer problem, right? So again, super common error. People put 0 on the right-hand side. So again, this is your buffer, right? Now the sodium chloride, I already know it is a neutral salt that's not going to screw up anything. So I'm not even going to worry about it in my ice table because it's not going to do anything, right? So sometimes best not to put numbers where you know you don't necessarily need to use them. But if you wanted to, it would be a 0 in this case. So I'll put a 0 there. The change in this case is also going to be a little bit different than what we've done previously in ice tables. And the change in this case is actually going to be the HCl. Because we made a buffer, we know that when we add that HCl, it should get used up by that buffer. So instead of using X's, we actually know what the change should be. By the way, it should always be the smaller number. And that's something to keep in mind, even though somewhere along the way you'll want to use the bigger number. That's going to be a minus 0.1 molar, our moles, 0.1 moles here. This will be plus 0.1 moles and plus 0.1 moles. And I am going to put some numbers there on the right-hand side. And what that's going to give me here at equilibrium is we're going to end up with what we hope should happen, 0 for our HCl because the buffers should use it up. We will end up with 0.9 moles of our sodium acetate, 1.1 moles, and we'll have 0.1 moles of our sodium chloride here. So we'll just put everybody in there just to show. All right, at this point, we've done it in moles. And again, that is one of the big differences in sort of our X's is we kind of already know what the X is. So we're going to actually use the number. And I would say that is probably pretty typical when you do an ice table with moles. You probably will know what the change is, and you will actually use a number rather than X in this case. As I mentioned before, at this point, it is really a good idea to convert these moles back into molarity. And we would do that by taking our total volume at this point. And in this case, we're going to keep our total volume at 1 liter, but you normally wouldn't. So for example, if you had 20 mils of buffer and you added 5 mils of acid, your total volume would be 25 mils at the end here. But just for this example, we're keeping it constant at 1 liter. So that means technically we'd come back here and divide each of these by 1 liter. And again, at this point, you technically would be using your total volume really of what you did. That will give us here 0.9 molar. That'll give us 1.1 molar. And that will also give us 0.1 molar. So now if you put numbers all through here, you will see a couple of things. And if you're not sure what to do at this point, you should look at your ice table and you should look at really what you have left over at this point. And if we look at what we have left over, we have sodium acetate, we have acetic acid, and we really do have sodium chloride left over. So we'll start with the far column here, which is sodium chloride. And we know already, as I just mentioned, sodium chloride is a neutral salt, right? Which means, frankly, it's not going to affect the pH. So we really don't even need to worry about it, right? Because it is neutral. So what that really leaves us left over is our sodium acetate and our acetic acid. And this is still a buffer, right? That is still our same buffer we started with, and we have that buffer left over at this point. So that means if I want to calculate the pH of my buffer after I added my acid, I also have two options as to how I could do it. Again, if you wanted to do an ice table at this point, you could. And again, you would set it up the exact same way as we did here, except obviously you would have your appropriate concentrations in the initial up here. So you could definitely do the ice table with the acetic acid. But since it is still a buffer, why not go still into our Henderson-Hasselbalch, which is what I'm going to do. And in this case, our pKa value is the same as we had before, is 4.74, and that comes from minus the log of our Ka value like we did on part A, plus the log of our base. So once again, we want to be careful here. Our base is actually this guy, right? And our acid is this guy, right? So we want to make sure we have those correct. So that's going to give us 0.9 over 1.1. And now if we put that into our calculator, 0.9 divided by 1.1, going to take a log of it and add it to 4.74. Going to get us a pH of 4.65. Yeah. First off, any questions on that there? Now, did our buffer work? Well, we originally started with a pH of 4.74, right? Before we added anything. When we added acid, it went from 4.74 to 4.65. That is not a big giant jump in pH, right? It didn't drop dramatically. But what it did do is it did move in the correct direction, right? It went down because we added acid, right? So if you did this calculation, you end up with a pH higher than 4.74 and you added acid, you're going in the wrong direction. So something is not right in that case. And again, I would say sometimes people screw up on the pluses on this side as well, and they do kind of minuses on both sides. So that's common too. Any questions on that? Now, earlier, just to demonstrate the idea of buffer capacity, we'll borrow this guy here. Let's say we have this same, let's say we have this same buffer here, right? And, you know, we were going to add our 0.1 moles or molar of our acid, and we went there to the table, the shelf, and we grabbed, you know, by mistake, our 18 molar hydrochloric acid, right? So let's see what happens in this case, right? Accidents happen, I suppose. Hopefully not too much. All right. So, all right, we wanted to add 0.1 molar, but you know, the 18 molar was 2 steps closer, so we grabbed that bottle. And if I added my 18 molar by accident, that would give me 18 moles, right, of hydrochloric acid. I just added to that just a little. What happens now in terms of the change? Who is kind of like the limiting reagent in this case? It is the sodium acetate, the smaller number, right? This sodium acetate, you only have about 1 mole of base to handle any acid coming in, and you just dumped in there 18 moles of it, right? No way it's going to be able to handle it. It's going to do its best, right? Which means it's going to try to use it up. So you're only going to get like a 1 mole action out of this. And again, you always choose a smaller number plus 1 mole. That means when you're done, you will have 17 moles of your hydrochloric acid, none of your base of your buffer left. You'll end up with 2 moles of this. And again, we're not going to worry about the sodium chloride in terms of pH. So basically at this point, if we convert this back into molarity divided by the total volume, we got 17 molar of this guy. We got 2 molar of this guy. So what do we have left in this situation is we do not have these two guys left, which are a buffer. We actually now have a weak acid and a strong acid, right? By the way, that is not a buffer, right? Even though you have two numbers, they are not related to each other. You basically have a weak acid and a strong acid, and this strong acid at 17 molar is going to produce a heck of a lot of H plus, right? And you basically just blew through your buffer, and you would see a giant jump in or drop in pH, really, in this case, because of that. So that's what we're talking about, sort of buffer capacity. You only have so many moles of your buffer in that solution to handle whatever is coming in to react with it. And again, that's why when you're making a buffer, you want to think about, what is the concentration of what I'm adding, how many moles of like H plus something can put in there when I'm adding acid, or OH minus when I'm adding base, and is my buffer sort of strong enough, if you will, to handle that influx of acid. And again, in this extreme case, it obviously wouldn't be. It would be able to you blow right through it. Again, it would do its best. It would use up as much of that base as you can, but at some point you're just going to kind of blow through it. And my little picture was crashing out, and now all you're doing is just adding a lot of H plus really quickly. Any questions on that there? All right. So when we try this one here, calculate the pH of a 0.3 molar ammonia, 0.36 molar ammonium chloride system. What is the pH before and after you add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer? In this case, we are not holding volumes constant or anything like that. And let me give you a number that might be helpful here. We'll go with the Ka for NH4 plus is 5.6 times 10 to the minus 10. All right, so we'll give it a go there, see what you come up with. Looking for two answers before and after we add the sodium hydroxide. And again, we're not holding volumes constant, so you do have to obviously take that into account. Okay, I think we'll continue with this on next time, or towards the end.